Alright, this is section 15.5, and we're going to talk about, I always called it the ideal gas law, and that's what I'll probably call it most of the time. Our book called it the universal gas law. Here's our objectives. We want to be able to use this equation, the ideal gas law equation, PV equals nRT. So here's our equation. If we're talking about this, the N stands for number of moles. So this is kind of the first of these equations that we've had where we have anything to do with moles, or you could have grams and then convert to moles. You have that. So anytime that you have that kind of an problem, you need to use this equation. R is simply a constant, and it depends, on what you use for your pressure, volume, and temperature. Well, temperature is always going to be Kelvin, and N is always moles, but what you use for your pressure is probably the one that changes the most. I like using this one, which is SI, so I like using the kilopascals, and it's 8.32 kilopascals times liters over moles times Kelvin. And it's kind of it's a weird label just so that everything cancels out when you do this. I do not expect you to memorize this problem that constant. I will give that to you on the test, so don't worry about that. Test or quiz or anything you ever need it for, I'll give it to you for whatever you are working with. All right, so let's do a problem. Let's take a look at this. It says a sample of nitrogen gas has a volume of 5.56 liters at 0 degrees Celsius, pressure 1.5 atmospheres. Now notice this one's in atmospheres, so we have to use a different R value. So in this one, I'm going to use the R value that goes with atmospheres, which is 0.0821. And it says the question is how many moles of nitrogen are present. So we're trying to figure out moles. Now the toughest part of this, using this isn't really a tough equation, but it's trying to figure out, okay, are we using the PV equals nRT equation, or are we using PV over T? Which one are we doing? This is why I always like to write everything out that I have. Notice that if I do that, if I write this out, I don't ever have any V2s, T2s, P2s, any of those things. I do have something that's asking for moles, which that's N. And so that hopefully guides me to thinking that, hey, I'm going to use my PV equals nRT equation. So then just plug everything in. Okay, so 1.5 atmospheres, volume is 5.56 liters. It's going to equal N. That's what we're trying to find. R we know is 0.0821, and I'm going to leave the label off because I don't have enough space. And temperature, and this is where you got to make sure, once again, like everything else, you got to change to Kelvin. So this would be 273 K. And then, just multiply all this stuff out. The way that I would do this is I would say, hey, 1.5 times 5.56, and then I divide by 0.0821, and then I hit divide by 273, and I get, for number of moles, 0.372. Okay. Now, if you don't understand exactly what I did there, just do the algebra like you normally would do. Divide this, both sides by 0.0821, 273, and do that on both sides. That's what I'm talking about. Okay. All right, so that should give you that answer right there. All right, I want you to stop the video and use this one, but notice that this one it asks you what the pressure is. Let's do the pressure in kilopascals because I just think that makes sense to do it in SI terms. If that's the case, this is my R value that I am going to use. So go ahead and stop the video now, and then I'll work through the problem with you in a little bit. All right, so if you write in everything that you see once again there's no other pressure, volume, temperature ones. We have everything except for a pressure, and it looks like we got P, V, T, and N, and so therefore, we're going to use our PV equals nRT equation. We've got everything except for pressure. Of course, R is always a constant, so we can use that. Okay, so plug it in. So we've got pressure, we don't know. So we're going to put V, P, volume 5.0 liters. N is 2.0 moles. R is 8.31. And our temperature, remember, convert to Kelvin, so it's 373 K. And we're going to take, I'm going to take the right side, 2 times 8.31 times 373 divided by 5. And I get pressure equals 1239.85. If we go significant digits, looks like it'd be like 1240. And that would be kilopascals. Okay. Alright, in section 15.6, there's just one thing that I really want to make sure that you're familiar with, and that's called Dalton's law of partial pressures. And what it says is, if you add up all of the pressures of individual gases in a container, and you'll get the total. So like, for instance, if we took a container of gas and we measured it and we found out that it had 75 kilopascals of, let's say that was nitrogen, and then we also had like 19 kilopascals of pressure of oxygen, and then let's say it was 2 kilopascals of pressure of CO2. So if we measured each of these gases individually, these would be the individual pressures. These would be what they call the partial pressures. And if we put all of those in one container, then we would just simply add them all up. So 75 plus 19 plus 2. So what would that be? 96 kilopascals total pressure. So whatever it is, whatever the different parts, partial parts of each one of those are, total them up, and that's going to give you your total pressure there. And that's all there is to it. So that's our next equation. There's one more we're going to do,